Good afternoon, all of you. My screen is visible. Hello, anybody? Hello. Anybody is there? Venu, Vinay,
Yes, sir. Audible, sir, your voice.
screen. Screen is visible, no?
Visible, sir.
Okay. In the previous class, we discussed different kinds of arrangement. Actually, why we need to discuss this kind of arrangement? Only thing is we need to decide what is the valve rating. That is the more important issue there. Different configurations may require as a different valve rating. If valve rating is more, then automatically cost of the valve will be high. That is the reason we need to identify what is the suitable rating of valve is required for the particular connection. So in that scenario, we discussed half wave and full wave, all these things. Only thing is we will see that what is the valve rating is required. In this for full wave, our expression EM, you will get it as 1.571 VD and output voltage is 0.637 EM. Actually, to find valve rating, what we required is peak inverse voltage as well as the average current is required. The rating of the valve is equal to the peak inverse voltage into average current rating. That is the actual valve rating. Now here in this case, let you can see that full wave midpoint converter we observed in theory part also, normally in power electronics and all. Once there is a midpoint is used, we can get it as a full winding is connected across the device when the device is under off state. So that obviously as a reverse voltage will appear across that. That is the inverse voltage. In a midpoint full wave rectifier, upper half is Vm, lower half is Vm, totally 2 Vm is going to connect. You can see that this one is a 2 Vm, is the peak inverse voltage is a 2 Vm in case of a midpoint full bridge. But normal rectifier, that is a full wave rectifier or a fully controlled rectifier, it is a bridge type, means you will get only the peak inverse voltage is a Vm. In that case, what will happen? The same load, uh, whatever load you want to connect, for the particular load case, midpoint converter is required as a high rating of the device. That is the major drawback also. Obviously cost. When you want to use some application, the particular load, we need to use as a valves also. In that valve, for midpoint configuration if you adapt, then you will get it as a more rating of the thyristors need to install. But whereas in the same load, if you connect as a bridge type configuration, then your rating of the device is going to be minimized because peak inverse voltage will be less. When bridge type is peak inverse voltage is Vm, whereas in case of midpoint type, they will get as a 2 Vm. So that is the reason automatically cost of the midpoint converter valve rating is more as well as the cost more. In this is the case, we can see here average current is id by 2 because two valves are there, then you can get it as average current is id by 2. Valve rating means you have to decide the valve rating of the converter is a product of inverse voltage into the average load current. IO, output current, AVG is the average. So peak inverse voltage into average current will give valve rating. So in this case you can see that in midpoint converter peak inverse voltage is a 2m and the current is a id by 2, means average current of a valve is id by 2, then 2 will get cancelled. The valve rating is em into id. In this transformer windings are not utilizing properly because your actual winding is Vm and Vm, 2 Vm is there, but what is the valve rating? We can observe that Em into Id, that is the case of what you call it as valve rating in the midpoint converter. Now we can see that bridge rectifier case, any circuit you can use it, this one or this one, only just different neutral point you can take it. And when the bridge configuration is there, continuous pulses are continuous output will be getting. Positive of cycle one set of the devices will conduct, and negative of cycle another set of the devices will conduct, and that's the reason we shown you as a current also, id current for when t1 is conducting, and then id current when t2 is conducting, or a diode, anything, just it is only the representation of a converter model. So here also you just find what is the valve rating. This is already just theory part I explained already, and you can see here average output voltage is 2 Vm by pi, and now peak inverse voltage is only Vm here. So in this case peak inverse voltage is Vm when comparatively midpoint converter. In midpoint converter peak inverse voltage is a V 2 Vm, but whereas bridge type there is a Vm, and average current also can the total current two set of devices, I1 I2 together will fire, then the current is id, and similarly I3 I4 will fire and that current is id. So then what you called as average current is id by 2. Therefore valve rating is the peak inverse voltage into load current. So what is the peak inverse voltage here? In this case is a Vm, and now id by 2. Then what is your valve rating is a 1 by 2 or a 0.5 Vm into id. But whereas in the previous case we are using as a 2 valves only, but valve rating requirement is there Vm into id. In case of RVM or EM, anything is same based on your representation. Valve rating is more in case of a midpoint converter, there we call it as a EM into id. But now in this case valve rating is a Vm into id by 2. So that means half of the valve rating is going to be required in case of a bridge rectifier. Then automatically valve rating is half, then what I can get it, there is a what you call it as a rating, value or a cost of that valve is a less, because once if you are using as a high peak inverse voltage, then the rating of the valve will be more, then automatically cost of that will be more. But only one more thing is here, somehow can compensate when compared to the midpoint, and this valve rating may be half, but what will happen, the number of devices are the also will differ some extent. When we compare to midpoint, there we are using as only two valves, but in bridge rectifiers we required as a four valves. That is the another problem in this case. But one advantage you can say that each valve rating is reduced to half when comparatively midpoint, but the same load we are operating, and this configuration is cheaper because valve rating is less. Whereas midpoint case configuration is costly. Valve rating is peak inverse voltage is 2 Vm. So it has to withstand that much voltage without conducting when the device are in the off state. So if the voltage across the device is something more than this breaker voltage, automatically device is going to be conducting the reverse side also, but it should not be. So you prevent that. We need to maintain wall rating must be greater than the peak inverse voltage, so that it will avoid the conduction during the reverse bias condition. In this case, just we observe now there is half of that when compared to the midpoint case. Use of high voltage application where the peak inverse voltage limiting factor, you can use this type of configuration. But whereas in midpoint peak inverse voltage is 2 Vm, it has to withstand. But whereas here the peak inverse voltage is only the Vm, so therefore for a very high application, automatically inverse voltage will be less. You can able to use this kind of rectifiers configuration, or you can say that. And the three-phase rectifier also is another configuration, because normally what we discussed so far is why that different configurations, what is the problem, and wall voltage rating, all these things will differ. But whereas practically if we use in the HVDC transmission and all, three-phase rectifiers also going to be used. In this three-phase rectifier, we can observe that when the T1 will fire or TRD anything, only our intention is to conduct the devices under forward bias condition. Let it be, if it is a diode, we don't require any firing pulse to that. At omega t is equal to 30 degrees, T1 will fire and it will continue to conduct up to the 60 degrees. Again the T2 will conduct, and after 16 degrees again T3 is going to be conduct. This is the sequence. Once if any of the device is conducting, then what is the output voltage? We can see here. In this case, if you start somewhere a phase, let it be it goes like this, then R, L, it goes to the output voltage is a VD, and then you can come to the neutral. So here you can you can connect any of the thing, depends on your requirement. At moment you can see there is output in the transmission line, just transmitting in a DC fashion. So after rectifier station, or this is a converter station, you will get it as a output voltage is a DC. Similarly, if D2 is conducting the neutral, then D2 L and VDC to the neutral. So like that, voltage across that winding is a EB, first winding is EA, this winding is a EC. For any particular valve is going to fire, your output voltage is similar to that. And once the device is conducting, automatically voltage drop across that device is a less, so you just make it as a short circuited there once device is conducting. And so anyhow this is we covered in power electronics also. But in configuration side you can see this is the three-phase supply. Let it be A, B, C. All the three phases are there. In that all the three phases, whenever it will give as a positive at this crossover point, you can see this. Just a minute, I will take pencil. Just I will share on screen. Yeah. In this case, you can see here once the device is conducting, from where to where device is conducting here, this is the point. Now it is not a thyristors, I am using as a diodes here, that's why firing pulse is not required, only it required is a forward bias. So at this point, this crossover point and this crossover and so on, you can able to get it as a forward bias. So this point is for B phase, this is for A phase, and this is for C phase. So whenever this phase voltage is more positive, then you can say that this device will be forward bias. Once this device is forward bias, it will flow current will be like this, and this phase voltage is going to be appear in the load side. So that is the reason you can notice there the shaded portion. This is a thick line. This is your output voltage waveform. And what is the observation is here? There is a 3 pulses are there in the output. So what is the pulse here? One full cycle of a AC supply, how many pulses are obtained in a output? So that we call it as a pulse number, or you can say that. And here you can see that once the device is conducting, the output voltage will be 0. Once the device is open state, then voltage across the device depends upon our voltage is available across that voltage. So this shows as a once the device is conducting, what will happen? The device is open, what will happen? It will represent as a output voltage as well as the wall voltages. And similarly, the current, if we represent when the current is present, when the switch is on, automatically current will be passes through that, and it carries the current. Because of the current, it will continue to conduct how long the current is available. Because once the device is forward bias, until unless the gate voltage is reaches to 0, this is going to be get current reaches to 0, it is going to be conduct. But whereas here you can see that the diode case also same logic. Once the device is conducting, then it will carry the load current, and other currents you can show it as a 0, because only one at a time is going to be conduct. And whereas the 2, the device 2 means D2 is conducting from this point to this point. Once this is conducting, it makes the reverse bias the diode D2 will make the reverse bias the diode D1, and so on. You can able to get it what you call it as output voltage waveform with different instant. But I represented the current also during what instant the current is going to be available, or you can say that from the crossover to the next crossover, current is there for the I1, means I1 device is conducting, it carries the current, whereas I2 is conducting, again it carries the current, and so on. So you can able to represent this. Now you can able to find what is the valve rating. So once if you identify valve rating, you can easily find this I mean, if you know the peak inverse voltage and average current, we can easily find the value rating. Once the value rating is low, automatically cost of that device will be low. And here peak inverse voltage in a 3-phase case, root 3 into Vm, and then average current, it is a 3-phase converter, then ID by 3. So then we will get it as a what you call it as peak inverse voltage you are going to calculate. So I mean value rating. So peak inverse voltage is root 3 times Vm into, just can calculate the value rating. Value rating is equal to you can see that root 3 Vm into ID by 3. So this will get root, then Vm ID into this will get cancelled, denominator here it will get as a root 3. So this is the value rating of a 3-phase rectifier, and that's what I mentioned here. There is a output voltage, peak inverse voltage, root 3 Vm, load current ID by 3, valve rating is nothing but a peak inverse voltage into ID naught V. This peak inverse voltage root 3, then ID by 3, you will get it as a peak inverse voltage, I mean valve rating. And this derivation also known to you. suppose if I consider only valve 1, at what the particular instant what will happen? Valve 1, if I consider 0 to 120 degrees, it is a conducting mode, you will get it as a 0, and 120 to 240 there is a reverse voltage, and then 240 to 360 it will get it as a 240 to 360 EA minus EC, 120 to 240 EA minus EB. So that means once the valve is in the conducting state, during this you can see it is a 0, and if it is in the open state, which is the anode is connected to which phase and cathode is connected to which phase, across that you can easily measure from positive to the negative. So therefore it is anode to cathode ratio. So then we can easily get it what is the value of valve rating by considering as a three-phase midpoint converter. Then another one is you can see analysis of a HVDC converter. So now this is another topic, and in that subtopics we will one by one we can go through. So today we will discuss, that is all about what is the previous discussion. There is a different kind of configuration. Now we will see the analysis of converter. There is a pulse number, because in a based on the configuration we can able to decide how many pulse numbers are required in this. And another one is a choice of converter configuration, because whatever things are explained, the different kinds, that is the which one is going to be better one. And so if you apply previous one, we notice the some of the things are what you call it as drawbacks, and some of the advantages are there. In that case, what is the better configuration? Just for that, what is the procedure we need to see, that you can able to find. And then another, that is a choice of configuration, and another one is analysis of a grid circuit, that is a 6 pulse and 12 pulse converter, and the converter bridge characteristics, and these are all the things we will discuss. Now we'll start with the pulse number. In a pulse number, this we can start normally. What is meaning of pulse? So pulse is nothing but a there is a one full cycle of AC supply. We can able to get it as a what you call it as how many pulses in a output. Suppose if AC supply is there, we can see that there is a positive half cycle and negative half cycle, but I'm in according to this diagram I'm telling. In this diagram, whenever anode is more positive with respect to the cathode, the thyristor 1 or a valve 1 is going to be conducting. If valve 1 is conducting, then you can see that only one pulse converter is obtained. Our intention is to maintain the VD is constant with the desired voltage. So that is only our requirement. In this aspect, we can see one thing. There is a here just you can see I am using as a source. Let it be Vm sin Vm cos omega t, based on the at what instant you want to take it, and accordingly it will change. So let it be this is a source, and you can consider this one is a valve. So once there is a valve, now if the valve is conducting, what is your output voltage? Once the valve is conducting, you will get only, suppose during this instant, if you see input is AC supply, this is our one cycle just I'm taking, and if valve at what instant it is conducting, like if alpha is 0 or alpha is 30 degrees, anything you can take it, this is our output voltage one valve is conducting. And when you compare to the DC supply, normally it is having as a more ripple. We are not getting as a pure DC voltage waveform in this case. And now you will move on to something is another tuple, one more same setup. If you connected in parallel, then what will happen in the parallel case? Voltage is maintained constant, but only the thing is we have to make sure that the current rating will be increased in that fashion. And also one valve will, if you observe, if that is conducting, your output voltage will be like this, but it is a lot of ripple content is takes place. But if I am adding one more one, so that means you can see like this. Then why I am adding there is a plus 1. So you can see that em cos omega t, and this is em cos omega t plus pi. What is it reason? Once if this is a positive voltage, let it be this one is a positive, it will the thyristor T1 will conduct. So after that instant this T2 is going to be conduct, and so on so forth. So you can able to connect that many number of walls, because one wall cannot be withstand, so that we have to connect the more number of walls, or you can improve the current waveform or ripple magnitude. You can connect the number of walls in parallel. Then what is output voltage if I connect like this? So your output voltage at any instant, this will conduct, and once it is 0, and there is a another one is going to is going to be second one is connecting. And now we can see this at this instant. If we compare these two, this waveform and this waveform, automatically second waveform is going to be better when comparatively first one. So first one is having as a more ripple content, and second one also there, but when comparatively previous one, this is going to be better. And why I am adding plus 1? So this is a 2 pulse converter. So how many degrees each device is going to be conduct? One pulse converter, let it be only one instant, it is going to be conduct. And then there is a 2 pulse converter, the total is a 360. That means pi is 180 plus 180, there is a 360 degrees divided by 2. Then what will happen? You will get it as a pi. So this starting it will conduct, then after pi it is going to conduct as a next device. Let it be, this is a thyristor is going to be 5. And similarly you can add one more, let it be as a 3 pulse converter. This is a 2 pulse converter, and that is the reason we are getting as a 2 pi by 2. 2 will get cancelled. We can add as a pi here, or according to the glance the output voltage, on the positive output voltage will conduct only one device, negative output voltage will conduct in the sense. Here is very small logic. You can see that which one is going to be fired based on the voltage magnitude. That means very straight away you can see there is a switch here, something, and there is a one voltage source, and here is a another switch or a wall, whatever notation you want to say, and there is a voltage, and that's also. Now this is equal to that only, and now there is a T1, there is a T2, and here is some 20 volts. Let's consider this is a 30 volt. Just for simplicity I taken as a DC supply. You want me just AC supply also, same logic more or less. Now when this is 20 and this is 30, automatically this device is going to be fired, and once this is fired, this will make as a reverse bias. So that way you can able to connect the devices are in series or in parallel, depends upon our requirement. And that's what I mentioned some of the things. If I compare the first one and second one, there is a improvement is there, many number of such circuits in parallel, so that improvement. And now and so on, that is what the previous one is 2 pulse converter. And if I consider as a 3 pulse converter, what is I'm intend to say is how the pulse number you can decide based on your configuration and all. That's what I mean to say. Now we can observe that first one is going to be fire at something 0 instant, and second one is a minus 2 pi by 3. So what is that 2 pi by 3? Here you can see that there is a what you call it as 360 by 3, that will give as a 2 pi by 3 and so on. We can connect many number of, so there is a, we can see that 2 pi by 3 we are obtaining here. Once the 3 pulse converter is connected, only 3 parallel set or walls are connected. Like that you can connect some q number of walls. depends upon your what you call it as valve voltages as well as the current ripple reduction. Based on that you can connect this. We call it as a basic commutation group. We can connect many number of valves are in parallel to improve their current rating, to maintain the voltage in the constant. You can connect like this. This is a for the P pulse converter or a Q pulse converter defined. I am connecting. This is a one valve, two valve, and so on. There is a three valves I represented there. Like that, if I connect some Q number of valves and so on and so forth, just I mention one, two, and so on. Finally, there is a so 2 pi by q based on, because 2 pi is a 360, based on number of pulses. If it is a 2 pulse by 2, 3 pulse by 3, and so on, so you'll get it as a 2 pi by q. This is the basic commutation group. So now in this case the many number of valves are connected in parallel. This is a one set of group. I call it as a basic commutation group. And in practically instead of using only this arrangement, you will connect as a winding. So here there is a transformer winding. You can connect this winding. There is a valve 1 winding, valve 2 winding, and so on. You will connect as a, for better performance in the practical case, you can connect as a large inductor series with that to maintain in the voltage. Also you have to maintain constant in the output side. That is a constant voltage transmission need to takes place. This is a basic commutation group. The combination of set of 1, 2, 3, and so on up to q number of valves are connected in parallel. So that is only the definition I mentioned there. Group of valves in which only one conducts at a time. There is a parallel. It should not be fire all the devices at a time. Only depends on the voltage across that. I mean voltage in the anode side, it will conduct. Whether it is going to fire in this what you call it as valve 1 or valve 2 and so on. That is a basic commutation group. That means a commutation group is defined as group of valves in which only one conducts at a time. And here how many you have to connect and what is the pulse number actually. So there is a q valves are in basic commutation group. This all together is called as a basic commutation group. It is not a total number of valves. So this is only one box, or you can say that it consisting of a q number of valves. How many valves? The q number of valves are connected in parallel, and now r number of valves are connected in series, I mean parallel. And like that, if you connect this setup, there is another same setup we connect like this, another same setup if we connect like this. This is a one group. This total set I call it as a one basic commutation group. Same, this is a second basic commutation group, and so on and so forth. Like this you can add many number up to some s number of commutation groups are connected in series. This is all about seriously we connected as a commutation group. Let to increase the voltage level we connected in series. Then this total set I call it as a only one series connected as a system. But like that, to improve our current waveform, you can able to connect this number of groups connected in parallel also. How many you have to connect it in parallel? Let it be r number of sets. So let it be, this is one basic group, and there is another basic group, and so on. You can get it as a there is, we can say that 1, 2, and 3. You can consider this is a one seriously. Like that you can connect total another basic set. There is a parallelly the setup is going to be there. This is another, and so on. You can get it. So 1, 2, 3, and so on. This is a 1, and there is a, and so on. How many you have to connect it in parallel? There is r number of basic groups are connected in parallel, and inside this there is a q number of valves are there. q number of valves are connected in parallel, mean in a basic group, and like that of the basic group s number is connected in series, and so on. This total setup is connected in parallel. How many you have to connect it? So let it be as a r number of group setup connected in a parallel. So this is what we can able to conclude in this point. There is a r of these connected are in parallel and s of them are connected in series. Therefore, finally, how many pulse? I told initially, if I use one thyristor, it is a one pulse. Similarly, if I use two thyristor, you are getting two pulse. Three thyristor, you are getting as a three pulse. And now it is not individually. Now we connected this setup in the different configuration. Therefore, total pulse number is nothing but a, there is a q and then r and s. So q is number of walls, r is number, these basic groups are connected in parallel, and that many basic groups are connected in series is a s. So therefore, if we can able to know what is the number of pulses in a particular system, we can represent this is the way p is equal to qrs. So that we can represent as a pulse number. At any instant, I already mentioned, only one device is going to be at any particular instant, only one device is going to be conduct at a instant. So that is the reason you can see here what will happen. We named this is a particular circuit. The circuit has a q such combinations of thyristors and the voltages. So we call this is a basic commutation group. Only this setup I call it as a basic commutation group. The idea is try to get or build a circuit which has a waveform on a DC side is close to the desired waveform, that is constant voltage. Because if you are increasing the number of pulses, automatically your waveform is going to be improved. So that is the reason we can see that this setup we are connected such a way that to get it as a constant voltage or a desired voltage in the output side. And so we try to connect such basic commutation groups many like that. So I represented diagrammatically, so one basic commutation group consisting of a q number of walls. That type of group commutation groups are connected in series and parallel to get it as a better operation. Suppose I take many such basic commutation groups are in series and parallel to get a very general converter, and also can build the converter. So by using this configuration we are building, so that intention is to get close to the DC side voltage, that is also very large values for the kind of pulse number. If your pulse number increases, that also initial in the second unit itself, initial class I mentioned a 1 pulse converter, what is the waveform, 2 pulse, 6 pulse, 3 pulse, 6 pulse, 12 pulse and so on. By increasing the pulse number, automatically what will happen, the improvement in the current waveform as well as the ripple magnitude is going to decrease, and then to avoid the discontinuity you can able to increase the pulse number, but beyond the 12 pulse it is not a preferable one. Generation of firing pulses, that is a little bit complicated. So that is the reason. And now this is our connection. There is, what is this blocks? It is a basic commutation group. In this it consisting of a q number of walls, and that setup you can connect many number of basic commutation groups is connected into some s number. S is in the series, this basic similarly this setup you can connect it in parallelly also, and not only one leg, you can increase, that will be in the many number of leg, so to get it as a DC output voltage. So this is our configuration. This configuration I represented P is equal to QRS. So this is our configuration. Same thing I mentioned here also. What is the pulse number mean? To generate the output, one full cycle of AC supply, how many pulses are generated in output, that we call it as a pulse number. And similarly, it converts AC to DC, involves switching sequence on different sinusoidal voltage onto the DC side. Obviously, the switching instants are different. The voltage waveform also will differ. Output voltage of the converter consisting of a DC component and ripple, and whose frequencies determine the pulse number. That means, suppose if it is a let's consider 6 pulse converter. Now, what is the ripple frequency? 6 times of that frequency. So that we can represent as a ripple frequency. Now, if it is a pulse number is more, the ripple frequency content will be more, but ripple magnitude will be decreases. Ripple frequency content is more means time duration is very less than during that. We can say that ripple frequency will be more, and ripple magnitude is going to be decreases. And one possible configuration for the P-pulse converter, just I shown whatever in the previous. We can represent this is the basic configuration, and so on. You can connect many number of walls in a basic converter, and the wall can be treated as a controllable switch, because whatever switch I shown here, this is not ordinary switches. It is a controllable switch, preferably as a thyristors in this case, because we are using as a large ratings. That is the reason we should go with thyristor. Turn on at any instant, provide the voltage across, it is a positive. And similarly, voltage source are obtained from a transformer secondary winding. The opening of the switch occur at the current 0. So that means the winding, primary winding and secondary windings are there. And the secondary winding is connected to the, what you call it as, to the load side and wall side. There is a transfer supply and then transformer, then the transformer secondary winding is connected to the wall. So that is the case of wall. So once the valve is open, then what will happen? Voltage across that will belongs to the source, and current will be the 0. Correct, current is 0. Once it is open, automatically current is going to be 0. And that is all about the pulse number. And second one is a choice of converter configuration. Now in this case, same as the previous one, the configuration for a given pulse number is selected in such a way that both the value of valve and transformer utilization factor are maximized. TUF is nothing but a transformer utilization factor. The given pulse number you have to select such a way that valve and TUF, transformer utilization factor, are to be maximized. So you have to maximize that. In general, converter configuration can be defined by the basic commutation group, and number of such groups are connected in series and parallel. That's only the so far the previous slides I explained. P is equal to QRS. That is nothing but a configuration of the converter. It consisting of a what you call it as a Q number of walls. That setup you can connect many number of devices. In that case, you can see that basic commutation group, a number of such groups are connected in series or in parallel. So this is the way we can represent here. One basic commutation group, and then 2, 3 and so on. S is the series here, and same set of these we can connect to the what you call it as load side. Or you can see that 1, 1, 1, 2 and so on, 1 are in the sense this basic group, and second and third and so on up to series, to maintain the load voltage is equal to the desired voltage. That many number of basic commutation groups are connected in series, and once if it connected in series, then that type of setups you have to connect it in parallel to maintain the constant current and improve current rating. And finally, you can able to get our VD with a high accurate fashion, because we connected number of are in series or in parallel. And now we can see this what you call it as a valve rating. So valve rating is nothing but a, we can notice previously peak inverse voltage into average current. That is only will decide the valve rating. Now you can see that valve rating is specified in terms of peak inverse voltage. It has to withstand the rain. Now valve rating, whatever they are, whether it is a 20 volts or 30 volts or 30 kV, all these things we have to decide by this valve rating. If that valve voltage has to be withstand the peak inverse voltage, so such a way that you have to connect as a valve rating. Otherwise, what will happen? The device will conduct automatically without giving as a firing pulses also. So now in this case you can see output voltage. What is this formula? You can see that normally if any waveform, I mentioned that output voltage is equal to for one cycle or one pulse you are going to integrate. Now what is S here, what is Q here? So Q is the number of walls, so automatically that many are connected in parallel, and S is a number of basic commutation groups are connected in series. So therefore all together is number of pulses only. So that's why we can make use of that is S into Q by 2 pi, and limits you can take it either it is a 0 to that or minus pi by q to plus pi by q, that is equal to Vm sin omega t. If you want to change that limit 0 to pi by q, you can use 2, and you can simplify this 0 to pi by q em sin omega tm will write outside, and integral cos will give a sine and substitute the limit 0 to pi by q. Why pi by q? Because that a q number of walls are connected in parallel, whether it is a one wall converter or a two wall converter or whatever, therefore that will decide the conduction interval. And if I substitute it, we can get it as a, our expression is S Q Em by pi into sine of pi by q. Only the simple substitution, integral cos will give the sign and substitute the limit, will get it as a valve rating. So this is the valve rating is required based on your pulse connected in a valves or in parallel, because valve 1, valve 2 and so on connected in parallel, and you can easily find what is the required valve rating. And similarly, peak inverse voltage across the wall can be obtained if Q is an even, because there is a even number as well as the odd numbers are there. If Q is even, then the peak inverse voltage occur when the wall with the phase displacement of pi is conducting, and this is given by, you can represent 2 Vm. So this is the Q is equal to even. Suppose if Q is equal to odd, then you can get it as a peak inverse voltage is 2m cos pi by 2q. So when the q is even, peak inverse voltage is this one, and q is odd, peak inverse voltage is this one. Then wall utilization factor is the given by the ratio between the peak inverse to the average, that is the wall utilization factor will be obtained whether it is a even or a odd. If it is even, you can use the upper 2em, PIV will use as a 2em, or if it is a even, you can 2em cos pi by 2q, you can use it. That is only the thing. Now utilization factor is given by, if for a q is even, PIV by VDO or V out, whatever. So then you simply substitute this 2m, I can represent this, and VTO I already derived in the previous version by substitution of 0 to pi by q and all, you got this. So and simply this ratio you can take it. Once if I take this ratio, you can get it 2 pi by sq, because this em and this em and this em is get cancelled out. So therefore 2 pi by sq, because this pi will go in the numerator, and 2 pi by sq sine pi by q. So this is the voltage, I mean valve utilization factor for q is equal to even. And for q is equal to r, what is the formula I have to use? This formula I have to use it, and this can simplify that. You will get it as a, what is our value for q is equal to odd instant. So this is the case of valve rating. And similarly, the utilization factor is different in 6 pulse converter configuration, because we know the formula for even as well as the odd, and you can try to find the different valve configuration, because you may connect many basic commutated circuit are connected in series, maybe 2, or parallel maybe 5, or a different configuration. You can use that way and find that what is the utilization factor. You can notice here Q, these are the two, means two walls are in parallel, means in walls are in parallel, and that basic circuit, only one basic circuit is connected in series, and in parallel, that basic circuit is connected in parallel is one, and this many number of are in series. Yes, it's in series, and like that, if you change this configuration, QRS is equal to P, then the transformer utilization factor, that is a wall utilization factor, VUF, peak inverse voltage divided by average, you will get it. These are the values. From this it is very easy to observe that the wall 1 and 3 are in the better, because this is a PIV by DV. It is not the actual rating, it is a utilization factor. If this is minimum, that will give as a better utilization factor, where because it is approaches to the unity, you are able to utilize properly. So that is the different here. And now we can see that transformer rating, whatever we observed so far, it is a utilization factor, that is a wall utilization factor, and then this one is a transformer rating, because we are using in the transformer also in the source side, on source and followed by transformer and followed by the converter in the HVDC scenario. And in this case, current rating of a valve is given by ID by R into root Q. As you know that what is the ID, load current, and R is connected in parallel, and Q is the number of valves are in connected in the parallel stream, that is number of valve, you can say that. When ID is in the DC current, which assumed to be constant, because it is a ID load current is assumed to be constant, the transformer rating on the wall side is given by, transformer rating is S. So S is nothing but a voltage into current aspect, and here multiplied by the pulse number, EM into root 2, and divided by EM by root 2 into IV. So that is a transformer rating on the wall side. And another one is a P. There is a I substituted as IV. So what is IV? ID by R into root Q. And then we can represent this is equal to EM we obtained from the VD naught expression. In that VD naught is equal to something expression is there in the previous one, and from the VD naught, like 2 Vm by pi into something. So in that case, we can get it as Em is equal to VD naught into pi by that denominator. So that will give as a this Em replacement. You can see that this Em is going to be replaced with this one, and you can get it as a transformer rating. And just you can simplify. How to simplify here? It is very simple simplification. We can see that there is a P, and this one is equal to Q R S. This is a R, and this is a Q, and this is a S. So then what will happen? You can able to cancel out this P with this three terms. P is equal to Q R S, and there is a root Q will be remains. You can make use of that root Q, and then VD naught into pi, this will be remains, and ID divided by the denominator factor. So this is our transformer rating. And similarly, you can see the different way. The cause P is equal to 6. Then what is the formula? P is equal to number of pulses. You can see here, let P that is equal to QRS. This is our formula, R and S. P is equal to QRS, Q is equal to 3, and R is equal to 1, S is equal to 2. So 3 into 2, 6 into 1, 6. Therefore, P is equal to 6. Then what is the transformer utilization factor? In the previously we observed no utilization factor, same ratio. We can see in the previously we discussed one statement here. Just see this. Yeah, so utilization factor is a peak inverse voltage by VD naught. Similarly, in this case, what you call it as transformer utilization factor is a rating of that is a STV, the transformer ratio, and that is what STV we observed, and divided by VD naught into ID naught will give as a utilization factor. So in this we just substitute what is the Q value, what is the R value and S value. We'll get it as utilization factor is equal to 1.481. Just simple substitution and sign up pi by 3 and root 3, all these things you can make use of that. We'll get it as a what is the transformer utilization factor, and the transformer utilization factor can be improved further. What will happen normally, there is a winding we have to use there in the basic commutation circuit. I've shown you a wall below which there is a winding, but in the each half, because in the 6 pulse converter if I consider, let you can see our diagram in the 6 pulse converter. Here is a one device and here is another device. Let it be like this. We have no means these are the devices whatever I mentioned as a gap. Here is one device, here is another device, here is another. There is a 6 devices in a basic circuit. What I used is here is a transformer, and for each case there is a winding. If I use separate winding in the first wall and then second wall, and what will happen is instead of this, if I use the combined this, so only one winding can utilize this group of the devices as well as this group of devices, so that we can able to improve further. That's what I mentioned can be improved if two wall groups, means upper group of the device and then lower group of the device, two groups, this is a positive group, or you can say that in our power electronics also we noticed in the full control rectifier, if we connect as a input is AC supply, then you can see that positive group and then negative group can share a single transformer winding. Instead of using as a two windings, if I share the single transformer winding, it is going to be better performance. That means in case current rating of the winding can be increased, because why we need to increase the current rating of a transformer there, because total the upper group and lower group is carried by that only, therefore root 2 times is going to be improved, and automatically while decreasing the number of windings by the factor of 2. So if you are reducing that, you can able to increase the factor of 2, current rating can increase. That is the reason you can mention here STV by VD naught and ID naught we already calculated 1.047. For the 6 pulse converter can be easily arranged by positive group and then negative group with a single winding. So this is the fashion you can represent it in the single transformer winding can able to operate in the total is it is a one leg. So we can use this, that is upper is VD by 2 and lower is VD by 2, total is a VD you are going to obtain. That is the choice of configuration. And then there is a HVDC transmission series conduction of a converter group has preferred because we can see that control and protection as well as the requirement of high voltage rating we are going to connect in the series, because to improve the high voltage. And whereas in the 12 pulse converter you can see the two are in 6 pulse converter or 2 in bridge converter connected in the series connections. But if you operate as a 12 pulse converter, there is a 30-degree phase displacement between the two set of converters, that is a 6 pulse converter and plus 6 pulse converter. We need to connect in the displacement of 30 degrees achieved by the transformer connection. How we will get the displacement of 30 degrees is one converter connected in the star fashion and another converter connected in a star delta fashion, so that we will get it as a phase displacement of a 30 degrees. And 12 pulse converter is preferable over a 6 pulse converter because the reduction in the filtering requirement. Why filtering requirement is reduced? Because once the what you call it as two converters are connected in a series fashion, the number of pulses are more, that is a 12 pulse converter, the waveform will be smoother. So when you are seeing 1 pulse converter waveform and 2 pulse converter waveform, so this is nearly just as the pulse durations are very small, you can represent that this will be as very smooth. If we pass that in through inductor, we'll get it little bit in the straight line fashion. Therefore, requirement of the filters will be minimum when compared to the 6 pulse under. So, however, increase the pulse number beyond 12 is not a practical case, because I told no, there is a complication in the harmonic, and normally in the generation of pulse itself has a complication. Designing of the firing circuit also complicated, and the non-characteristic harmonics in what you call it as are not eliminated, because these all harmonic analysis will come in filtering, and harmonic will be in the consequent units will come, but preferably beyond 12 pulse converter is not a preferable. So this is the today's class, then we'll see the next class. If you have any doubt, you can ask me, otherwise you can give the attendance and can leave.